try and share your screen, Ran.
Yeah, one sec. See my screen, right?
It's starting to share.
Okay, good. Right, so there are not that many of us, and the presentation is not overly long. So if you have any questions, just interrupt whenever. Right, so I'll be telling you about something I've been working on for the last few years and I'm still working on, which is enabling lossy transport for large-scale AI. And it all starts from trying to convince companies that they should depart with what I call the lossless abstraction, right? So the lossless abstraction, which is how most companies currently work, basically you can summarize it as everything sent shall be received, right? So whatever you send over the network is responsible to deliver it, right? So we have this clean separation between the AI models that decide what they want to send and when, and we have the network that has to deliver it, right? So that's the current state of things. And particularly what this means is that if we lose something, if we lose a packet, we have to retransmit it, right? We have to get this data transferred. So before I tell you what's wrong with this approach, since I don't know what's the background of people here, I have a few slides, like very high level, about how model training is working. I will be focusing almost only about model training. Towards the end, I'll talk a bit about inference. So back in the day, we used to train models using an algorithm I'm sure you all know called gradient descent. So we have our model, we had our data. We would go over all the examples in the data. We will compute the loss. We will compute the gradient, the direction in which if we change the weight a bit, we can minimize the loss. We will update the model and we will continue. Right. And the idea is that if the loss surface looks somewhat reasonable, each time we will minimize the loss until hopefully we will end up in some place where the loss is small and we have good accuracy for the model. Now, obviously, there's a problem here, which is each time we need to go over all of the data, it takes a lot of time. So the first step is to switch from doing gradient descent to stochastic gradient descent. This is probably 100 years old now. So instead of going over the entire data, each time we will look at the batch. We will compute the gradient just for the batch, update the model, and continue. Now that worked fine for several decades until at some point, even computing this for the batch took too long. At which point we move to what's called data parallel training, right? So instead of training it using one GPU or one worker, we may have multiple. Each of them would have their own copy of the model. Each of them would have a shard of the data, right? So we're splitting the data between the different workers. And now at each step, each worker looks at the batch, computes the gradient. They're all doing it at the same time. This is how we can get the speed up compared to doing it in one place. The only thing is that once we're done computing the gradients, we need to somehow aggregate them, right? So our idea was that in this example, maybe we wanted to look at a batch of size 16, but each worker was only looking at a batch of size 4. We have 4 workers, so we need to somehow aggregate the 4 gradients that we have. And this is a step called gradient synchronization. Now, what is the challenge of gradient synchronization, right? And this is a figure taken from a paper by NVIDIA that was in NSDI this year. Right, so here you could see on the x-axis is the time it takes to do gradient synchronization. I don't remember the setup that they have. They have it in the paper. This is one specific experiment where they looked at what's the CDF of doing this gradient synchronization. And what they observed is that you have a significant gap between let's say, the median time and the 99th percentile, right? So we have here a very, very long tail. So sometimes this gradient synchronization can take a lot more than usual. And the problem is we cannot start the next training iteration until we're done with the gradient synchronization. Right? So why do we have this? Right? So there are several reasons for that. So one of them is that we can have packet drops that I think we talked about already. And this could be due to either congestion or corruption. We could have queue buildups that just inflate the latency. We can have accelerator failures. We can have switch failures. We can have link failures. We can have straggler nodes, so some nodes can take longer than others. And that's a very incomplete list. My point in having this list here is that I want to emphasize that, oh wait, so there's one more thing, which is all of these become much worse if you're trying to do training at a large scale, which doesn't fit in a single physical location, right? If you're trying to do training over a wide area, everything becomes even harder, all of these problems. So, and the common thing about all of these problems is that they happen almost completely due to system events. And what I mean by that is it's not, it doesn't matter how you sample the data, right? So it doesn't happen because you sampled a bad batch of data that this happens. So the processing time is largely independent from the actual data that we're running on, which is important, as I'm gonna explain in a bit. Right, so what do I propose that we do instead, right? So I claim that we should embrace loss, right? So instead of forcing everything to be delivered, we can get some flexibility. If we're talking about training, then in the gradient synchronization phase, that will help us cut this tail latency that we saw in the CDF earlier. Right? Now, what I'm going to propose is going to add some loss, right? So it doesn't come for free, right? So far, there has been a lot of research on how to optimize gradient synchronization when we don't allow loss, right? But now, if we do allow loss, then we need to make sure that this does not affect or does not significantly affect the accuracy of the model that we're training, because otherwise this is all pointless. So we need to formalize what loss we're allowing, and we need to make sure that the amount of loss that we add is not too much in some sense. Okay, so why do we think that allowing loss makes sense? Well, for one, we already have some loss built in to this process, which is we're not doing gradient descent, right? So we're not looking at the actual gradient of the entire data, we're sampling batches, right? So even by doing that, we already have some loss. So we already have some noisy estimate of the true gradient. And what we're going to see is that we can have other types of losses that will translate to system benefits for optimizing the gradient synchronization step. And we can compensate for it. So for example, one option would be to increase the size of the batch, right? So maybe instead of having 4 examples per worker in the local batch, we can have 6, 8, right? So it will take a bit longer to do the local processing, but now if we aggregate the result, we will have a better estimate of the true gradient, and maybe then we can use some of this extra loss that we can add to match the initial loss to optimize the performance. And when I'm saying increase the batch size, it could be either in terms of the local batch size, or we can just increase the number of workers. That's also an option. Okay, so let me give you a few examples of what I mean by adding loss to the training process. Right, so this is a suggestion we had a few years ago in a paper that was mostly theoretical. And there, our suggestion was quite simple. Or I'm simplifying things a lot, but for the purpose of this talk, all we wanted to do is to say, look, losing packets is a problem. We are currently retransmitting them. If we just avoid retransmission, if we just avoid lost packets, that's also not very good because some parts of the gradients are important. So you can think of specific entries that influence the gradient a lot, for example. And what we proposed there was, before we even start the transmission, we can encode all of the coordinates together. Right? Specifically, we use the randomized Hadamard transform, but it doesn't really matter. So basically, we're encoding all of the coordinates together. And now we're sending the data, and we're ignoring lost packets, right? So every time you lose a packet, so you're missing some of the entries of the gradient after you apply this transform, you just estimate it as 0, which is like, I don't know what it is. Right? And we can actually analyze this, right? So we talked about how what we care about is how good is our estimate of the true gradient. Well, we know how this affected, right? So we know how if you lost some fraction of the packets, how this will affect the true noise that you would get, right? And this very same idea was actually adopted later by NVIDIA in the Dissolved reduced paper that I mentioned, right? So this idea of encoding all of the coordinates together, ignoring loss, estimating this as 0. Okay, let's look at another example, which was from a paper in NSDI last year. And the idea that was quite simple. So we said, look, we have some straggler nodes in our system. Maybe some of them take longer than others. What if we ignore them, right? So what if we ignore those that take too long? And if you think about it, this is essentially the same as decreasing the batch size because of what we said earlier, that the reasons for the tail latency are independent of the data. So the fact that I'm now ignoring, let's say, 10% of my workers is the same as decreasing the batch size by 10%, because it's independent from the examples that they sample for the batch. So that was one of the suggestions in this paper. We evaluated it. We saw that we had a very small test bed. That's a challenge of evaluating something like this in an academic setting. But we saw that if you're, I think we had 10 workers in this experiment. So even if you're not waiting for 30% of the slowest workers, then that's still fine in terms of what's the accuracy that you're getting for the same number of rounds. Let me give you another example, which is what do we do when there's congestion, right? So congestion at least increases the latency of the packets that are sent in the network. In a worst case, they can even get some congestion drops, and it's not always avoidable, right? So it depends on your setup. It depends on whether you own the cluster or whether you have multiple jobs running concurrently. You cannot always avoid congestion. Now, our idea was that what if whenever there's congestion, the switch that sees the congestion will just compress the data, right? So we send it, let's say, at full precision, which may be not 32 bits per entry, but the precision that we use for the training. And then if there's congestion in the network, well, the switch can just compress it, right? So that was the idea. And we also asked, like, can we do this with existing hardware switches, right? So Clearly, you can try to do something like this with, if you have like a programmable switch, if you have a Tofino, you can implement some algorithms on the switch. We wanted to do it using other switches as well, right? So we're not even assuming a programmable switches here. So let me explain how this works. Right? So our setup was that we have some background traffic, right? So maybe we have multiple training jobs running, maybe we're sharing the clusters with other users. So we have some background traffic. We have some switch in the middle of the network that is forwarding packets. Then we have our training job, right? So we have a GPU, let's say, encoding the gradients for the gradient synchronization, but they're sharing the network, right? So both types of packets get queued in the same queue at the switch. And maybe we have multiple of these workers all using the same queue at the same time. Now, something that is supported by many of the current switches, and I suspect that quite soon it will be all of the hardware switches because it's part of the Ultra Ethernet transport spec, if you're familiar with it, is something called packet trimming, right? So whenever there's congestion, what happens is that the switch sees that the buffer fills over some threshold, right? And then what it does is it starts trimming packets. So trimming packets basically means we're discarding most of the payload. And then we're going to send the remainder, which is a header and a small part of the payload. And we're going to send it to the receiver. And we're going to prioritize it, right? So it's going to get higher priority than the standard traffic. And the idea is this, right? So the switch streams the packet, it sends it at a high priority to the receiver. The packet makes it sooner to the receiver. The receiver would NAC the packet so that the sender can resend it. And then if you have something like packet spraying, it can even take a different path in the network. And sometimes it can even reach it before if it was queued in the original switch, right? Just because maybe this path is loaded, the other passes are less loaded. Maybe we can improve it this way, right? So our idea here was this, right? So let's assume that this is happening, right? So let's assume that the switches in the network, they don't have to be programmable, but they are following this strategy of trimming packets whenever they see congestion. And our idea here was that maybe we can use the part of the packet that does make it to the receiver, right? So if you look here at this illustration, then there's going to be a part of the payload that's not trimmed. The reason for this is that the switches can only trim it to what's called the cell size. I believe in the current Broadcom switches, it's something like 200 something bytes, right? So it's a bit more than the number of bytes we have for the header itself. So we have some extra bytes that are currently not really useful, but we can use as the compressed form of the data, right? And since this was like a hotnets paper, it wasn't like a real system, all we said was like, let's take the most significant bit of each entry, let's put it at the beginning of the packet, right after the packet header, right? And then if the packet gets trimmed, right? So if the switch sees congestion, it trims the packet, and then only what's above this cut line gets delivered, then the receiver can see this one bit only, like this most significant bit for each entry. But you can think of it as this is already a signal, right, that we can use. And if we put this together with this idea of encoding the data together using this randomized Hadamard transform, We can even make sure that if you have a small number of lost packets, then the accuracy across the gradient just degrades slightly, but you get very good estimates of all the entries in your gradient, right? So we assume that the switches are doing that. We just encode the packet differently, and now when the receiver gets it, it can estimate the data. We don't need retransmission. It may still let the sender know that the packet got trimmed because maybe we don't want to use this path going forward. So depending on how you're doing your load balancing or your packet sparing, you may just decide not to use this entropy value. If you pick a different one, maybe your ECMP would route it in a different path. But our goal was not to have to wait for the retransmission. Right, so we saw a few examples, and now the question is, how much loss can we allow or should we allow, right? So all of these add some noise, right? So we have an inferior estimate of the true gradient. It has some system benefits, like maybe we don't have to wait for all workers, maybe we don't have to wait for retransmissions. But how much is a good amount of loss to allow the system? So those of you that are familiar with the theory of stochastic gradient descent and the more fancy optimizers that are similar to it, know that at least that when you're thinking about the guaranteed convergence rate, right? So what happens in practice, it's not that clear, but if you think of the guarantee of how many training iterations you need to do before the process converges, you would see this quantity comes up there, right? So it depends on the expected value of the squared norm of the noise, right? So how far you are from estimating the true gradient. And then if we have multiple options on how to use this loss to improve the system aspects, then we can ask what happens if we have more than one of these in parallel. And actually, we always have one, assuming we're doing stochastic gradient descent, right? Because we're always sampling batches to begin with. So now we're asking, what if we add to that this idea of in-network compression, or we add to that the idea of not waiting for all workers? Right? So we have several of these, and now we wanted to know what happens when we combine them. So we, in the original theory paper, we also have this theoretical result, which says if you have two lossy operators, and it could be one of them is just like sampling a batch, the other one would be one of the suggestions we saw earlier. And you know how much noise each of these add individually, then we can bound how much noise they add if you run both of them in parallel. And there's an assumption here that the processes are independent of each other, but I think like this is true for the most part, right? Because if we're sampling batches and we said like it does not affect the system aspect of which nodes are slower or which packets get lost, then they are likely to be independent from each other. So we can use this theory to understand what happens when we allow multiple loss sources altogether.
So Ran, just for clarification, is
Yeah.
A and B, are they different kinds of loss inducing processes?
Yeah.
Okay.
Yeah. So if we want to look closer at to what this means here, is that we have two lossy processes, right? So one of them can be sampling a batch from the stochastic gradient descent. One of them can be, let's say, the in-network compression, right? And if we know what is the noise we have from each of them independently, if the other didn't exist, right? So we know how to estimate the noise of sampling a batch. We know how to estimate the noise of the in-network compression, then what this theory tells us is how would the loss look like if we enable both of them at the same time, right? And for many of these suggestions, we can actually analyze this quantity analytically, right? So we don't need experiments to do that. I think I mentioned this for not doing retransmissions after doing the randomized Hadamard transform, but we have similar bounds to many of these suggestions. Does that make sense?
Yeah, cool, thanks.
Yeah. Yeah, the second part here is not, it's like it shows that it's tight in some sense, right? So if you have strict bounds, if you know exactly how much noise, then this result is tight. If you only have upper bound on the noise, you can only get an upper bound on the noise, but this result is tight. Okay, so let's say we have this idea. We know how we can run multiple lossy operations together. We know how much noise they would add. But then we said, like, we need to contrast this with the inherent noise of running stochastic gradient descent, right? So how do we even know what is the noise that we have from sampling a batch? So it turns out that it's not that simple, right? So we have now a project on estimating this. And I think like this is sort of a solved problem when you assume that the training takes place on a single node, right? So if you have a single node, it can estimate quite well what's the noise that you get from sampling a batch of a given size. But now the challenge here when we're doing this data parallel training is that we have multiple workers. They each have their own sample batch. And we want to be able to estimate what would be the noise if we aggregate these local gradients without doing the naive thing of sending all of them to one place and running the standard estimate, because this is as expensive as doing gradient synchronization, right? So if our goal is to be able to optimize gradient synchronization by allowing some loss that is small compared to the inherent loss of the stochastic gradient descent, then we need to be able to do that without sending everything to one place and having it estimate this loss. Okay, so I don't have a good solution for this yet. We're looking at different options for that. So hopefully in a year from now, we'll know more about how to solve this. We're looking at different sketching approaches, dimension reduction approaches, but it does seem that by exchanging an amount of information that's going to be much smaller than the true size of the local gradients, we can estimate what's the inherent noise of the stochastic gradient descent, and we can use these to decide how much loss we're going to allow the different system optimizations that we allow. Okay, so far we talked about training. Let's talk a bit about other types of lossy transfers, because I think like the title here was lossy transfers or something, lossy network transport. So let's talk about what happens during inference, right? And specifically, I want to talk about what's happening during something that is very commonly used, which is called disaggregated inference. So in disaggregated inference, there's two very distinct steps, right? So one of them is called the prefill step, which is basically like you give it a prompt, you give your LLM a prompt, and then it processes it, right? And then we have our decode phase, which is where we generate the result, right? And the reason why the two are very different from each other is that during the prefill stage, we have all of the prompt available at the same time, right? So we can process it in a much more parallel way than during the decode phase, where each time we're generating the next token, right? So the decode phase is iterative, right? So each time we're generating one token. There's some new suggestions that try to do more clever things, but at a high level, that's how the decode phase works. And this means we need a lot less compute for the decode phase. So the idea of disaggregated LLM inference is that you put the prefill stage on a much stronger GPU, right? So you let it process the prompt in a much higher degree of parallelism. And then you send the result, which is called the KV cache, over the network to the decode worker, and the decode GPU or GPUs can be much weaker because they follow this iterative process of generating one token at a time, right? So what we're doing here is we have a suggestion of how we can allow some loss to the KV cache during this network transport to optimize the process of disaggregated inference. Another idea we're looking into is to mitigate the impact of corruption, right? So currently, as we said, whenever we're sending something, we assume that it makes it to the other side. So if we're sending a packet over the network, then even if one bit got flipped, so this we think of this entire packet as being corrupted, we're discarding it, and we're having the sender retransmit it. So we want currently to ensure that no bit goes corrupted, and this is usually done using checksums approach, right? So we have a checksum at the Ethernet level, we have a checksum at the RDMA level, and we're basically verifying that the actual content of the packet matches the checksum, and we think of it as suggesting that the packet is valid, and then we accept it, right? And if there's a mismatch, like if we have this bit flip somewhere, and now the checksum doesn't match, then we're retransmitting it, right? And you may think like this is a significant problem. It is to some degree, but we have a nice way of mitigating it, which is something called forward error correction. So this is quite commonly used these days. So instead of just relying on the network not to corrupt a single bit, we add some redundancy when we send the packets, and then as long as the receiver can recover all of the transmitted bits correctly, we don't need retransmissions. But it still happens, right? So it doesn't make this go away. It's like a trade-off, right? So now we add this redundancy to the packets, and we could still, in some point, if we're really unlucky, even the forward error correction cannot help us recover a corrupted packet, and we would have to retransmit it. Right, so what can we do instead? Well, we can say we don't care, right? Or maybe we shouldn't care about corruption. Now, clearly, you cannot just ignore everything in the packet and have all of the bits corrupted, because if you have, for example, a corruption at one of the header bits, the packet may not make it to the destination, right? So our suggestion is this, right? We want to separate the payload, the content of the packet, to what we call a protected part and a corruptible part, right? So the headers are always going to be protected. So we want to make sure that no error happens to the headers, because we want the packet to reach the correct destination. And then quite similarly to how we did it in the in-network compression idea, we can separate the content of the data to important bits and less important bits. and protect only the important bits using the checksums, right? So what do we gain from this? Then we could either lower further the probability of corruption, or we could use less redundancy in the forward error correcting bits. Okay, so let me try to summarize. This is going to be talking again about training. So what's my vision for training? So we're developing an understanding of how the different system optimization works. Our suggestion is to increase the batch size in some sense. So it could be either by increasing the number of workers or slightly increasing the local batch size, right? So maybe we can do a bit more compute, and this can give us a budget to run all of these ideas on how we can cut the tail latency that we saw as a problem at the beginning of the talk. And then there's always a question of how do we evaluate the benefit here, right? So let's say we have this suggestion. How do we know if it's any good, right? If it's helpful in practice? Then we do it by measuring the time it takes to train a model, right? So it looks something like this, right? So here you could see a figure where the y-axis is the accuracy of the model that we're training. Oh, it does hands up in Zoom. And the x-axis here is the time we took to train this model in minutes, right? The bottom figure is a zoom in on just the best options here. So this is taken from this THC paper that I mentioned earlier, where we ignored some of the stragglers. We actually did, that's not even the main point of this paper. All I wanted to show you here is how we measure the benefit, right? So if you look at the yellow curve, which is our baseline, right? So that's a common framework. I think it was originally by Uber that uses RDMA. RDMA is quite optimized, but it doesn't use any lossy transport, right? So it's delivering everything as is. And we compare this to our suggestions, the blue and red curves. One of them, we also did some in-network aggregation. The other one is not. That's the difference between the two. And we see that to train the model to approximately where it would reach like the final accuracy if we would train it without any lossy operation, we could reach the same accuracy much quicker, which allows us to deduct that this is useful, right? So we did cut the training time by something like 30%, and the final accuracy is the same, so this is beneficial. Okay, so let me summarize. And for the summary, I took an earlier version of this slide deck, and I think I gave it to ChatGPT or one of the other models, I'm not sure now. And I asked it to come up with an illustration that summarizes this talk, and that was the result, right? Which I liked, so I kept it. Yeah, so I think like if we lose the lossless abstraction, right? If we allow some loss during the training or inference process, we stand to gain quite a bit from it. And I will just add that this is actually a joint work with many other universities and companies. This is not all done at UCL. So I think that's all of my slides. So I'm happy to take any questions.
Excellent.
Run as a question. Run as a question.
I have a question. Yes.
The first hand raised is Ran's. Actually, I have a question. Is that the money or the ideas which was more important when you lose the lossless abstraction?
The money or
the idea? It looks like you get dollars and you get an idea and you get a network and two people shouting with their arms raised.
That's a good question. I need to ask the model that did it. I just gave it the slides, no other instructions other than create a figure that summarizes this.
Can I ask a couple of questions? Sorry, I cannot find my hand
Yeah,
before.
of course.
Ryan, I think we once discussed this with you. You explained me why you wouldn't use FEC. You mentioned FEC for packet corruption, but could you not use FEC for packet loss by doing FEC across packets and then not? I assume that's because you believe that the losses to be correlated, but I'd like just to hear a bit from you.
You can use it for congestion loss. Yeah, you're right. The issue is what happens if you now have congestion and the switch starts dropping packets and you're losing multiple consecutive packets, right? This is where the forward error correction cannot help you. Right?
Yeah,
So usually it can only help in a small window of packets around where you are right now in the transmission window.
But I mean, the switch is shifting flows to to several servers, right? Is there intuition that when you have losses that they're going to have a high probability of affecting the same flow?
Well, that's a good question. I think like if you have a good trimming system in place, then ideally what would happen is whenever congestion builds up, the switch will start trimming the packets, will forward it to the receivers, the receiver will NAC the packets, and then the senders will start using alternative passes, and that will alleviate the congestion. The question is how long this is going to take and how many packets a specific flow is losing in this process. I'm not sure.
Right. Or now, I was not even thinking of packet trimming at this stage. I was thinking you'll just do normal drops, but it will drop some packets, but hopefully not from the same flow, and you have enough redundancy on the FEC to recover the data. Anyway.
Yeah, I think like FEC is great when you have uncorrelated loss.
Right.
I'm not sure what happens when you have congestion loss. That could mean like I'm dropping a lot of the packets in a short time frame because I have incast or something.
Yeah. Sorry, final question. You mentioned SGD, but I think more elaborate optimizers like Adam, they use this thing like momentum, right? So where sometimes you go really fast because you're such a speed, and because you're increasing the gradients by a lot. I wonder if your little tricks might affect more than just SGD.
Yes, so we are also looking at other optimizers. I wanted to keep it similar because I don't know what's the background of
Yeah.
this here.
Okay.
Yeah, but we are looking at other optimizers as well.
Cool. Thank you.
So, and there are a couple of comments in the chat. I don't know if you can see it. Andrew is saying, is there any other places where lossless accommodation can happen is audio video live streams? Can you recycle some of your ideas there?
Yeah, I think there was something quite similar for, I don't remember if it was audio or for video, but there was a similar suggestion from that community as well. I think there they did not touch the network at all. They just said, if something happens in the network, we want not to have to wait to retransmit it. Let's try to decode it from what we have. So they have this, I think, like layered bitrate compression where if you're getting some of the packets, you can encode it as like a lower bitrate of the video or the audio. I don't remember which one.
And then Colin is saying how they did partial checksums for wipes. I don't know if you want to elaborate on that, Colin.
I'm not sure I want to say much about it. I was just struck by your slide with the corruptible packets and the partial checksums. Yeah, that one. The IETF did exactly this for voice over IP flows a long time ago. With they turn off the UDP checksum and have a checksum covering the headers and the first part of the packet, and a separate one for the rest. And It's exactly the same idea, but being applied for voice over IP. So yeah, it's always interesting. The same techniques come around for in radically different areas, and presumably at about a billion times the bit rates this time.
Yeah,
Yeah,
I've seen that. It's,
Kyle Jamieson also used to have something like this for Wi-Fi where they were
Yeah.
doing bitwise. Yeah. So. Yeah, and then Chris Walker is saying about radio astronomy correlation, which is apparently capable of dealing with drop packets, which is interesting.
How do they do that?
Well,
Chris, yeah.
so I had a conversation last week, and I mean, I say they're capable of dealing with lost packets. I think they just accept that they lose a little bit of the correlated data, but the fact that you've missed a little bit of the data doesn't seem to worry them, because you just integrate for a longer time. Is my, not being a radio astronomer, is my understanding.
I see. Yeah.
Cool. Any other questions from anyone? If not, well, happy Halloween, everyone.
Happy Halloween.
Scary Halloween, not happy.
Scary Halloween. Yeah. See you guys next
Yeah.
month. Yeah.
Thank you, Ran.
Bye. Thanks for organizing.
Thank you.
So, bye.